In this lecture, I'll be covering stress transformation. Let me explain what that is coming up. So we'll first tackle stress transformations in 2D. Sometimes it's useful to transform stresses and strains to predict failure, and we'll be discussing how we do that. So say I have a bar and I apply a load to that bar that's uniaxial. And I want to figure out what the stress state is on an inclined plane AA. So that's what I'm interested in. What is the stress state there? So what I could do is to form a new coordinate system, x prime and y prime, where x prime is the normal to this inclined plane, while y prime is the one tangential to the plane. Now notice that this area is slightly larger now, and the area is a x prime, while this area here is just a. So this area has grown in size a little bit because it's slanted, while if it was straight, it would be the same area as a. I'm going to consider that oblique angle that I'm looking at an angle theta. What is the objective? Is to find the stress state on this inclined plane. That's what I'm after, and that's what we'll be trying to do. So don't get worried about the amount of material here. We'll try to go it step by step. So if I were to look at this force P here, I can look at the reaction force on this oblique plane to see what's going on. That force P also should be the same amount because the summation of forces in the x direction is 0. If I take this force P and decompose it in the x prime direction and y prime direction, what I get is that this component here is P cosine theta, while this component here is minus P sine theta because it is in the opposite direction of y prime. So in this example, the components of the force P are in the x and y direction. Now, I will look then at the area A of this, the area A, AX, this area here, the cross-sectional area here, is really the area A divided by cosine theta. I'll let you do the math at home to show that. If this area is A and is slanted by theta degree, you can show that this area here that's slanted is A divided by cosine theta. We can check that. We can check that because if the theta was 0, then this will be straight. And you can see that cosine of 0 is 1, so the area AX is A, which is when this is straight. But it's slanted at an angle theta. So that's the area I'm looking at. So, but what is stress? Stress is the force P that's acting normal to this surface, P divided by the area, but the area is A divided by cosine theta. While this P here is P cosine theta. So I know P cosine theta. I know this slanted surface A, which is A divided by cosine theta. And that gives me that I have an area of P divided by A times cosine theta squared. Notice that this P over A is really XX cosine sigma XX cosine square theta. So that is how we can find the stress at an inclined plane at an angle theta. Let's look at the shear stress along the transform axis x prime. The shear stress is really tau xy, tau xy, but the prime. I'm looking at the shear stress tangential here. That is the shear stress P y prime divided by the area AX prime. This cross section is slightly bigger now. So then I have P sine theta divided by the slightly larger area, which is A divided by cosine theta. And then you get this is equal to minus P sine theta cosine theta divided by area. P divided by A is again sigma x. So I get sigma x sine theta cosine theta. So what I'm showing you here is we're able, if I know the stress sigma xx, which is P divided by area, this area, if I know that stress and I'm trying to find the stress in the inclined angle, I can tell you what the normal stress is and the shear stress is. and that's this stress, and that's this stress. So I can plot how sigma divided by sigma xx looks like when theta is varied from 0 to 90. And when you find this, that the stress will be equal to sigma xx at the beginning when theta is 0, which makes sense when it's not slanted. And then it will drop. While the shear will be 0 at the beginning, makes sense. If this was straight, if this incline phase was straight, and I was applying just a pure normal load P, there cannot be any shear. So it makes sense that that is 0 at the beginning when theta is 0. But it turns out it increases the maximum value of 45 degrees. So it turns out that the shear stress is the highest when this is at 45 degrees for you, the uniaxial case, this particular case. So now let's look at a more general situation. So let's consider plane stress condition. And when I say plane stress condition, these other stress states are 0. Anything with Z is 0. So usually that occurs. Plane stress usually occurs when the body is thin. So in that case, I'm just going to look at the XY plane. In the XY plane, I have sigma XX, sigma YY, and tau XY that shears that square. So what I'm going to do, I'm going to then take this right here and look again at an inclined plane, at an angle theta. So I have the new axis, which is xy prime and y prime at an angle theta from the x-axis. And I want to look at what is the shear stress at this orientation. Now, this is a little bit different from this problem, because in this problem, there's only one stress, which was the x direction. While in this problem, I'm looking at multiple things going on. I have sigma xx, sigma yy, but also the shear stress as well, combined, all that combined. So I want to look at what's going on at an angle that's inclined. Remember, that's what I'm after. So, in other words, I'm trying to figure out what the stress state is perpendicular to this surface and tangential to this surface. Exactly how you see it here. I'm also interested in what is going on at other inclined surfaces, but let's start with these two at least to see what's going on at this surface. So let's figure out how to do that. This is what I'll do. Let's start with a simple thing. Let's say that AB has a unit area 1, just to keep it simple. AB, this edge here, has a unit depth 1, but also the length is 1, such that the area AB is 1. It turns out that the area for QA is AB cosine theta, while this area here is AB sine theta. You guys can check that at home. So it's pure geometry. So this AB sine theta and this AB cosine theta, while this area is 1. So let's do a force balance in the X and Y plane. So let's do that. I have this PX here moving to the right. So that's PX. That has to be balanced by the only forces going to the left, which is tau XY and sigma XX. So let's look, sigma XX times this area here, which is AB cosine theta, which is this whole thing here. That's the area times sigma XX. That tells me the total force going to the left, plus the total force going to the left of tau XY times the area QB, which is AB sine theta. That's what I have here. So now let me look at the force going upwards, Py. This Py right here. Py is anything that's moving up or down. In this case, it's sigma yy going downwards. So that's sigma yy, Py equals sigma yy times AB sine theta. And the reason is because this area here is AB sine theta as shown here. Plus tau xy, which is going downwards also, times the area of that edge, which is QA, which is really AB cosine theta. That's what I have here as well. But I said earlier that AB will be a unit area. So that's why now you don't see AB showing up here. So that's the force balance in the X and Y plane. So I'll continue with the derivation. Now let's do a force balance on the slanted surface, just on this surface, to look at this carefully. What is going on here locally? So we see here that sigma x prime times AB is a force here going along perpendicular to this cross section. So sigma x prime times AB is a force going along the x prime axis, this x prime axis here. Okay, so that's that. But that has to be equal to, also has to be equal to px times cosine theta. And it also has to be equal to py sine theta. So this py projected in the x-axis and px projected in the x-axis, x prime axis, is going to have to be sigma x AB equals px cosine theta plus py sine theta, right? There's no other way. Like, I have this px and py. If I decompose them in the x direction, that has to be equal to sigma x prime. The same thing can be said with tau xy prime. I can look at that. Tau xy prime times AB, this edge, has to be equal to py here, which is going upwards, this angle, which is cosine theta, sorry, this projected along the y prime axis, which is this axis here, is py times cosine theta. And then I have this px, which projected in this axis, the xy prime axis, going downwards. So that's a negative of px sine theta, pure geometry. But AB is really 1, remember. Remember from the previous page that this is what we had. So this is what I had in the previous page when I did summation globally in the whole thing. Well, this is summation of forces on that slanted surface alone. So now I can use equations A and B and combine them. So if I substitute equations A into B, so I have px and py in terms of sigma xx and sigma yy, I can plug all that in here. And when I do, I get this way of relating sigma x prime and tau xy prime. I can relate that to the stresses that are acting on that square that we saw here, right? So again, remember, this is the stresses I know, but I'm looking at what is the stress in this inclined plane. And I want to look at the normal to that surface and tangential to that surface. These are the values I'm looking for. So I'm trying to figure out how to relate this to the original values that were provided on stress states. And I'm able to achieve this formula here, which I will not make you memorize, but you should know how it was derived at least and have it with you. You can actually find a sigma yy prime using the same procedure, very similar procedure. Or you can just take the theta that I have and add 90 degrees to figure what the sigma yy prime is here. That's another way of doing it. But you can also repeat the process that I just showed you. You can also use trigonometry identities. For example, 2 sine theta cosine theta is sine 2 theta. So you can make things simpler looking. And the same thing can be done with the cosine squares and make into cosine 2 theta. So this is just a manipulation to make things look simpler. That's all that is. But look at what the part I think you need to understand is what we have accomplished. And let me repeat it one more time what we accomplished. we were trying to figure out what is the stress state at an inclined plane, given the stress states here in this square. So this is how you relate the stresses in the inclined plane to the stresses in the original square that we saw. That's how you do a 2D transformation of stresses. Any so recall that this is what we had from this page here. We can find the sigma x prime at a slanted surface that's normal to the surface. And recall that if the shear stress in that particular inclined plane is 0 and you only have normal stresses, that becomes a principal stress. Recall that. But for now, let's say I want to find the maximum and minimum normal stress and at what angle it occurs. You can use go back to calculus and find the partial sigma x with respect to theta to figure that out. And when you do, you can solve for the max and minimum, and you get this equation here. This equation here actually turns out to be the principal stresses. So the max and minimum normal stresses at an angle occurs when the principal stresses do occur, and there's 0 shearing stresses. It turns out that that angle theta p can also be found with this equation. You can see that because tau xy has to be 0 at that inclined surface. So you can solve for theta in that equation. You can see that there. If I make tau 0, I can calculate theta, and so I get the tangent of theta, and you can see that there. Tangent 2 theta p equals 2 tau xy divided by sigma x minus sigma y. Because shear stresses have to be 0 at the inclined phase. So I'm able to get the max and minimum principal stress by taking this derivative equal to 0. So in other words, knowing the stresses here in this square, I can tell you exactly at what inclined plane there's the principal stress occurs, and I can tell you what angle, and I can tell you what magnitude. So in other words, these formulas are alternate approach, is a different way of doing it as what I had shown earlier with the eigenvalue problem, but they both give you the same answer. We can also find the maximum and minimum value of the shear stress at the inclined plane. So you start with the transformation equation that I had here. So the very bottom one here. And how do I find the maximum value of tau prime? I just take the derivative of tau prime with respect to theta, which is what I've done here, and set equal to 0. That gives me the tau max equals to the square root of this. And then you can find that you'll find actually that the location when that happens is tangent 2 theta s equals this equation. And that's how you find where the maximum occurs. You also find that when the maximum occurs, the maximum shear stress occurs, normal to that surface, you actually end up getting that the normal stress to that surface is the average of the stresses on each of the faces that we originally had, which is a very interesting thing, but it's the way it works out. In other words, let me go back. Sorry, it moved. So say I have a problem where this was 4, this was 5, this is 4, that's 5. When the average stress is what? 4 plus 5 divided by 2. That's 4.5. So this stress will be 4.5. So that's what we're talking about there. The normal stress to that surface. So what we're going to do an example on how you will do this, okay? So say I have the state of stress presented here, and I ask you about the principal planes and principal stresses. So one approach that taught you how to do this is, you know, this sigma xx, you know that this is, this right here is sigma xy, this one right here is sigma yy. So then you put your stress state like this, sigma xx, sigma yy, but it's negative because it's against the surface. And then you have 40 and 40 for sigma xy. That's your stress state. And you can turn this into an eigenvalue problem, like I had shown earlier. You can find the determinant of this, and that'll give you two characteristics roots, and that gives you the principal stresses. And you can find the associated principal planes in the first one and the second one for each of this. So that's going to give you the same answer as what you will find with this method. So let's look at how to do it with the formulas that we discussed. Is very straightforward. So again, let me read the problem statement. Given the stress states that we have here presented to you, what is the principal stress? I'll find the orientation of the principal stress by using the formula. I know tau xy, I know sigma x and sigma y, so I should be able to find theta p very quickly. So I just substitute it in. Tau xy is 40, sigma x is 50, sigma y is minus 10 because it's going against the surface, and that gives me 1.33. I use a calculator, and I get the theta p can occur at two different angles, 26.6 and 116 degrees. To determine principal stresses, I plug in sigma x and sigma y, which is what? Sigma x is 50, sigma y is minus 10. That gives me 40 divided by 2 is 20. This is going to be 60 divided by 2 is 30. Tau xy is 40. The square root of all this is 50 really. 20 plus minus 50 is going to give me either 70 or minus 30. So the maximum value is 70 and the minimum value is minus 30. So if I were to plot this, what I get is that theta p at 26 degrees gives me a maximum value of 70 here, while in this phase I get the minimum value is minus 30. And it's the way it's pointed. Obviously, there's no shear stresses because I calculate the max principal stresses. To calculate the maximum shear stresses, I plug in the values again, and I get 30 squared plus 40 squared, and that's 50. Notice that if I calculated this already, I can just use that. This right here is tau maximum. So I already did that, that's 50. So that's the maximum value that you get, which is 50. You can see it here. And the angle can be easily found. You can see using this formula here. Where is it? This formula here. You can use that formula. And when you use that formula, you will find that the angle is at an angle of 18.4 degrees. Finally, you can also find the stress that's normal to the surface. And what we said is find the average. So this is very interesting because the average is just sigma xx plus sigma yy divided by 2. So what is it? 50 minus 10 divided by 2, and that's 20. And that's exactly what is shown here in this page. So when the maximum stress occurs, the normal stress to the surface is only 20. So Quite simple. That is a process that is used to do the calculations. I actually did it here to show you, but you know, it's very simple and it's all there in the calculations, just using the formulas that I have provided. We can also use a Mohr circle to estimate the critical values using a graph. And it's a very convenient approach to use it. So given a known stress state of sigma xx, sigma yy, sigma xy, like I had shown, you can actually do a very quick way of doing this. The first step is to plot the points x and y in this circle here. So you'll plot sigma xx first and minus tau xy, and then you put sigma yy and plus tau xy, as you can show in this graph. The next step is to construct a circle centered at C. And the circle is going to be centered at a value of sigma x plus sigma y divided by 2. And the radius of the circle is going to be this. So very simple. Just simplifying the average of sigma xx and sigma y. Why? That tells you where it gets centered, while this one tells you the radius of the circle. You draw that circle, and where the intersections happen, that's going to be the principal stress, sigma min and sigma max. The angle between xy and the x-axis tells you the angle at which the principal stress occurs times 2. I'll do some examples soon. The principal stresses are obtained at A and B. So at this point and this point. While the angle is automatically found by finding the angle between xy and AB. So it's a graphical method to do this. You can also determine the stress state at other orientations with this method. Because you know the center at which is located, you know xy. If you want to look at an inclination 15 degrees, all you have to do is rotate the xy axis to twice the angle, and that'll give you the new coordinates for x prime and y prime, which will contain the stresses at different orientations. Remember, the stress state that goes here is written in this way, has to be written in this way. Why don't we now look at an example? So Mohr circle for centrical axial loading. If it's only axial load, then the only stress state is P over A. Sigma y in this case is 0. Shear stress is 0. So in this case, the average stress can be found. You can draw the circle and the dot here. And it's going to be sigma x plus sigma y divided by 2. So that's this point here. You can see sigma x goes from here to here. So therefore, when I put my dots x and y, because shear is 0, then you can see that it lies on this axis, x and y. So in this case, the intersection is such that the max principal stress is 0, the minimum value based on this circle, and x is going to be the maximum stress of P over A. If I look at torsional loading, a more complex loading condition, is pure shear, while sigma x and sigma y are 0. There's no sigma x or sigma y. When you do this calculation, you'll find that the center is right here in the middle. Because sigma x and sigma y is 0, 0 plus 0 is 0, divided by 2 is 0 still. So the center of the circle goes here. And if I were to plug in what the radius will be, since this 0, that's 0, divided by 2 is 0, square root of tau xy squared, it gives you tau xy. The radius becomes just tau xy. So the radius is tau xy. And so now you can see that your principal stress is this point A and this point B, as discussed earlier. So given the same stress rate I had before, let's use Mohr circle. So what am I supposed to do? I calculate the average of sigma xx and sigma yy. So sigma xx is 50. Sigma yy is minus 10 because it is against the surface. 50 minus 10 is 40 divided by 2 is 20. That's done. Now I have to calculate the radius. So 20 goes here at this point. The radius is using the formula I had showed you earlier, which is right here. Let me find it for you. Sigma x minus sigma y divided by 2 squared plus tau xy squared. In our example, sigma x minus sigma y gave us, this was what we got before, exactly what we got before, 50. So now all I have to do is to sum 20 plus 50, and I get this point, 70. And I subtract 20 from 50, and I get minus 30. That's this point. So the max principal stress is this point, and the minimum value is this point. So that's how you do find the max principal stress. But I can also plot where the XY line is, and that's very easy to find. The XY line is just following what I told you. The coordinates of this point is 50 and 40. 50 sigma xx, and tau is the y-axis, so it's minus 40 as shown here. That's exactly how we discussed it. This point is located using also 10, this one here, sigma y, and then the height is 40 again, but positive. So you're going to put one negative and then one positive, exactly how we showed here. So the angle between XY and AB tells you the angle of inclination of the principal, where the principal plane occurs. And the angle is 26 degrees. Okay, we've done sufficient examples. If I want to find the max shear stress, we just follow the same procedure as I discussed before, where I told you that tau max is equal to the radius. We discussed that earlier. And the normal stress is going to be equal to the sigma average, as I had discussed before, which is 20. The maximum shear stress will always occur at a 45-degree plus sigma theta p. So always, if I know the principal plane, I add 45, and that's when the shear stress occurs. Let's do example 3. So given the stress of 100 megapascals and 60 megapascals like this, and the shear stress in this case is negative, notice, is 100 or 48. I'm sorry, it's 48, but it's negative, while 160 is positive. So if I were to write this down, it will be like this. It will be 100 for sigma xx, 60 for sigma yy, minus 48 for sigma xy. Now all I have to do is to locate the center of that circle. That center is found by adding 100 plus 60 divided by 2. And that's 80. That's where this point is, 80. You can see that they plotted it here. So now I can calculate the radius. So the radius is going to be, basically, we discussed this before. First, one thing you can do is plot the points where X and Y go. So as discussed before, X is always going to be located at sigma xx, comma, minus tau xy, while Y will always be located at sigma yy, comma, tau xy, always. So this point is 60 minus 45, 8, and this point, 148. So you can find this distance and divide that by 2 to get the radius. You get that the radius is going to be 52. So therefore, if you take 80 and add 52 from this point to this point, you get the maximum principal stress. And if you take the center, which is at 80, and subtract 52, you get the minimum principal stress. So principal stress will be intersecting with the x-axis. But I know this orientation, so I can find this angle very easily. So therefore, I can find for you the principal plane where that occurs, which is half of that angle. I did it all over here already. I already did that visually for you. You get 132 for this point and 28 for this point. That's the max principal stress. You can also use the eigenvalue approach and you'll get the same answer.